Dear colleagues, we greet you. I greet you at the 5th One World YoungStatS webinar, first one after the holiday time. This webinar has arose in joint cooperation with the Young Researchers Committee of the Bernoulli Society, Immacurato, Sandro Gallo, and Chino, to whom we greatly thank for their cooperation and great involvement. The webinar will discuss important inequalities which form the ground for the mathematical work in machine learning and have been studied to a great extent in previous years, also in the work of today's discussant, Professor Gábor Lugosi. But I hope more would be explained later. YoungStatS project is part of the Young Statisticians Europe YSC initiative of the FinStats Federation of European National Statistical Societies Association, supported by both Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics, IMS. It consists of a blog where we publish recent contributions from leading journals. We just had a fresh upcoming contribution from Laurent Dadessy, Xavier Tehat-Fouly, and Yannick Guillaume-Varche, based on the recent Annals of Statistics publication, and a monthly webinar exclusively devoted to presenting most interesting younger scholars in statistics, probability, and econometrics on international level. Since its start, the webinar bears the prestigious One World label inspired by the One World Probability Seminar. Following today's webinar, there will follow webinars on symbolic data analysis in October, novel algebraic approaches to maximum likelihood estimation in November, and on difference in differences approaches in econometrics in December. I therefore welcome you to today's webinar and give now the floor to Dr. Ima Valentina Curato of the Young Researchers Committee of the Bernoulli Society. Thanks.
Thank André for the introduction. We are very happy that we could organize together with YoungStatS this web seminar. As André say, we are Young Researchers Committee in every possible sense, in the sense that we are a very youngest committee in the Bernoulli Society world. We are three representative. I am the representative from Europe, Sandro is the representative from South America, and Zenwa, that is not with us today, unfortunately, is the representative of Asia. We are members of the Bernoulli Society. For the people that do not know what this society is, this is a society for mathematical statistics and probability that organizes yearly worldwide workshop conferences to support connection between researchers. Obviously, you could decide to become a member of our society. If you are interested in doing so, I will post a link in the chat that you can give a look at it, where you find more information about our society, the benefit that come from being member of the Bernoulli Society, and also how to become member of our society. Of course, we are very interested in subscribers from young researchers, so PhD student, postdoc. You can become member of our society at a very, very low rate, so you don't have to pay a lot of money. And you can have access to all our workshop and events, and also to our young researchers community. If you just want to follow our activity, I will also post a Gmail address in the chat. You can write as an email, and we will put you in a mailing list and send you all information and all the events that we will organize as Young Researchers Committee in the next future. And now, without further ado, let us start our web seminar. The first speaker of today is Antoine Marquina. He has got a PhD in mathematics at the University of Versailles, Saint-Quentin, and Yvelines. I don't know if I said it right. I tried. And he's now, assistant professor at the University of Paris. He will present us a talk about concentration inequalities of suprema of unbounded empirical processes. So Antoine, the floor is yours.
Okay, thank you. So, okay, everybody see.
Yes, we can see it. It's perfect.
Okay. Okay. So, but I don't see my screen. Okay. Okay, so thank the organizer for the invitation. So I'm very pleased to present my quote at this web seminar. And so before starting, I prefer to warn you that I taught all day since 8 a.m. to 4 p.m. So I'm quite tired and with a less voice. So sorry about that, and sorry if I search my word, but with a mask all the day, it's quite difficult. So, I'm going to talk about concentration inequalities for suprema of empirical processes, and especially the unbounded case. So this talk is based on a paper which has the same title, which has been published a few days ago in Annals of Lobel. And so there are different points in this work. So the first one, it is more probabilist and concerns the method used to obtain concentration inequalities. This method I developed during my PhD, and I believe that it could be used in other situations which are important in statistics. And I think we can use it to obtain new inequalities for other objects like U processes or other objects in order to realize classical assumptions. But there are some work to do, and it is also ongoing research. Another point in this work is the result itself concerning the suprema of empirical processes. And this is a point that I will develop in this talk. I will try to explain what we are looking for and why this result is new and why it is important for the application. And the third point, which is in fact not in this work, concerns the application of the result, particularly in model selection. And in fact, it is ongoing research that I am doing with a colleague in France. So the idea is that the selection procedure is based on the minimization of a penalized criterion, and the penalty of which is calibrated by using deviation bounds of an empirical process. And but to be honest, these 2 last years, which are somehow complicated, we have taken some late, but we are making progress, but not so far. So I have to begin with some notation. Okay. So let x1 to xn be IRD random vectors with value in RT, where T is a countable index set. Okay, so for each k, the vector each k is the vector each kt for T in capital T. We assume that all the random variables are centered.
Antoine, you guys see the slide moving?
I'm not seeing. I'm just seeing the first
You
one.
not see the slide moving, Antoine.
I think it's because of the share screen you made, like you did the full screen, and you shared only the when you did the full screen. That's why we were able to see everything.
Ah yes.
So you need to stop sharing and share again, I think.
Okay. It's too complicated for me. I don't. Okay. Wait a minute. If I do this, but I don't see my screen.
Yeah, it works.
Okay.
Yeah.
Yeah. Okay.
Now it works.
Okay. Sorry. So here's the notation. I said that we assume that the random variables are centered. We denote by oh, okay, we denote by MK the envelope, that is the supremum of the absolute value of HKT for T in capital T. And we assume that the envelope is square integrable. So SNT is the sum of H1T to HNT, and we denote by Z the supremum of SNT for T in capital T. Okay. So the question is how to provide good upper bounds of the probability that Z minus C of Z is greater than H, and the probability that Z minus C of Z is lower than minus H. So how to control the left and right deviation of Z around its mean. So this is concentration inequality are an important tool in many domains, and a crucial tool in order to control the fluctuation, random fluctuation of many objects. For example, so non-parametric statistics, as I said at the beginning, also in random matrices, random graphs. Also, for example, in other adaptive methods in non-parametric statistics also leads to the control of the random fluctuation of an empirical process. So it is very important to have a good upper bounds of the deviation of to have good upper bounds to have good concentration inequalities. There are different methods over the years which has been developed to obtain concentration inequalities. So there are maternal methods, transport inequalities, Taledron's method, which is isoperimetric inequalities, and also the method introduced by Ledoux, which is entropy methods. So in this talk, I will not talk about the method I used, since it's more probabilist and it is much more technical, so it is not the subject, I think. But okay, I will say a few words in the talk. So in the title, I said the term unbounded. So I have to begin with what exists in the bounded case. So it's the merit of Taledron, who was the first to obtain a concentration inequalities for suprema of empirical processes in the bounded case. By bounded case, I mean that the random variables is
I guess we lost Antoine.
I hope the computer advertised him that he's not online anymore, because otherwise he will keep speaking alone.
Yeah, you did good. We completely lost him.
Maybe it did take place. Here it is.
Yes,
Okay, super.
sorry, the university in France has some problem.
Happens. I mean, really, these things are happening. Have happened often in this year, in the last year, unfortunately.
Sorry about that.
Try again. Yeah, go.
Okay, it's okay. Okay. So as I said, there is a set of paper from Boucheron, Lugosi, Bousquet, Klein, and Rio to obtain a good constant in the Taledron's inequality. So here a classical result in the bounded case, that is, we assume that HKT is lower than 1. And so we can see that this exponential inequality is a functional Bennett inequality. That is, the function h here is the function we find in the classical Bennett inequality for the sum of high-ID random variables. And in fact, in the application, when we use this result, the assumption that the SKT are lower than 1 implies some restriction in some assumption in the framework, in the statistical framework. For example, in the context of regression framework, we have to assume that, for example, that the regression function is bounded by non-constant, or we have to assume that the errors have exponential moments, and it poses some that. For example, in the context of model selection, the penalty involves some unpleasant quantities or irrelevant numerical constants or some drawbacks. And it is quite natural to ask if we can have such a result with not this condition that the SKT are bounded by a non-constant. And if we are looking in the literature, there are not so much work in the unbounded case. The works I'm aware of are the following. The first one of Bouchon, Bousquet, Lugosi, and Massard in 2005. They obtained a moment inequality, but it involves this quantity, which is defined as a weight variance. And we can see that in the moderate deviation bound, it is not the right behavior. We can see it later. 2008, Adam Schalk obtained Foot-Nagiev inequality, but he asked that some conditions on the tail which are semi-exponential. In 2014, Lederer and Vanderveer only require a moment of order P for the envelope, but the inequality is not around, the deviation is not around E of Z, like we want to have, but there is an extra term eta of E of Z, where eta is strictly positive, and then the constants are non-explicit, and also they are non-optimal. And in 2013 and 2015, Vanderveer, Lederer, and Dirksen assume some Bernstein type condition on the tail to derive exponential tail for Z. And their work are based on chaining arguments. And all this work are also based on the original work of Talleyrand and of Ledoux. That is, they used for functional analysis. For example, they use a truncation argument, and then they control the bounded part with the inequality in the bounded case, and then they require some tail assumption to control the Riemann term. And in fact, the starting point of my work is that we think that functional analysis is not a good way in order to obtain a concentration in the unbounded case more directly. And that's the reason why I focus in a new method to obtain more directly an inequality. So, okay, so I need some more notation. So let QX the quantile function of a random variable x, which is the inverse, general inverse of the tail inverse function of the tail function of the random variable x. So we have this variational formula. So when we want to obtain a concentration inequalities, we can upper bound the upper tail quantile function, and then we directly obtain a deviation for deviation inequality for x. And also we can use, we do not, often we prefer to upper bound not true X, but the inverse of the Lord Laplace transform of X. Why? Because first, this the inverse of Lord Laplace transform is greater than the Prandtl function, and it presents some advantages, which is first we have a simple variational formula, and we can see that we have only to upper bound the Lord Laplace transform of X to have an upper bound the inverse of the Lord Laplace transform. And also we have a useful tool, which is that it is the inverse of the Lord Laplace transform is subadditive in the random variables. Okay, so we can see this the inverse of the Lord Laplace transform as a generalized quantile. And in my work, we work not with this one, but with another generalized quantile, which presents the same advantages than this one. So this is the conditional value at risk, denoted by CVAR for short, which is defined by 1 over u times the integral from 0 to u of the tail quantile. If X has no atom at the point true H of u, the CVAR at point u is only the expectation of X conditionally to the fact that H is greater than true H of u. And so we have the same advantages. First, it is subadditive, and we have that the CVAR is greater than the upper tail quantile and is lower than the inverse of the Lord Laplace transform. So if we have an upper bound of this quantity, then we have an upper bound directly a deviation inequality. So to understand what inequalities we are looking for Z, since I want to obtain directly an inequality, I must have a goal. I must know what type of inequalities I am looking for. So since the empirical process and SNT converge in finite dimension towards Gaussian processes, we can look the deviation inequalities concerning the supremum of a Gaussian process. And so we all know the well-known inequality of Cyrulson, Ibragimov, and Sudakov, which compares the tail of a supremum of Gaussian process and the tail of Gaussian random variables. But in fact, in their papers, they have a more precise inequality, which compares the quantile of the supremum of Gaussian process and the quantile of Gaussian random variables. And with some calculation, which is not so hard, we can see that it implies that the CVAR of the supremum of the Gaussian process is lower than the CVAR of the Gaussian random variables. And then we can upper bound the CVAR of the Gaussian random variable by the inverse of the Lord Laplace transform, which is equal to the square root of 2 logarithm of 1 over u. So we want to generalize this inequality. Moreover, if the index set T contains only one element, Z just the sum of ID random variables, and so we want also to generalize this kind of inequality. And when the random variables only have a finite variance and only a moment of order P, the deviations are handled by a Fulton-Nagayev type inequality. And the inequality with best known constant have been established by Rio in 2017. It gives the result in terms of an upper bound of the CVAR of the sum of IID random variables. So here the Gaussian part, we can see that the constant 1 in front of the square root of 2n of an logarithm is optimal. And then there is a part here with u at the power -1 over p, which is also optimal, since we only assume that the random variables have a moment of order p. So we want to generalize this result of for some and this result for Gaussian processes, for supremum of Gaussian processes. So the result I obtain is the following: is a fault-Nagiaev type inequality. So we obtain an inequality of the CVAR, which directly imply an inequality, a deviation inequality on Z. So the first part here, the Gaussian part, we work over here the square root of 2n logarithm of 1 over u times the Wimpy variance, as we want, plus an additional term here that I will discuss just after. And then here the part, since we only assume that the envelope have a moment of order p, and we cover here the term u at the power -1 over p. And we have also a left deviation inequality. So this term Vn, we have to give some discussion about it. So I have it explicitly, and we can observe that in if we are looking at the asymptotic, we can see that the term Vn vanishes, and so we only have square root of n times the Wimpy variance. It is also known that in a non-asymptotic upper bound, we cannot expect here, we cannot expect that the term here is 0. We must have an additional term. It is something known. And I also give a useful and explicit upper bound of Vn defined in terms of this quantity, which is the expectation of the supremum of partial sum. So, so we have this inequality. And what it is interesting is that when we have a CLT theorem, Vn is at the order of n at the power -1.5 p -2 over p -1. And we can explicitly construct an example where we assume that the random variables have a power type tail, in which we show that the variance of Z minus the Wimpy variance is at least at the same order here. So the conclusion is that our term Vn in the inequality is of a correct order. So, and to be complete, the term here Ek in this upper bound, we can upper bound it if we use the local maximal inequalities for empirical processes. We can see the result of Van der Waart and Vellner in 2011, or Chanov-Zukov, Cheturikov, and Kato in 2015 to control this quantity. And so we are somehow happy with this inequality because it answers the question to obtain an inequality in the unbounded case. And for the application of this result in the context of model selection, it presents some difficulties, but we are, so as I said at the beginning, we are making progress. So we have to, the term Vn causes some problems, but since we have an explicit upper bound with explicit terms, it is, we think that we can make it, we are sure that we are leading to a useful to a great conclusion. But it presents some difficulties since new terms that we do not that different that we can see in the previous literature. And what I want to say also that in fact I do not really need the independence of the random variables h1 to hn. I need some exchangeability of the variables, and we think that we can replace the independence by some dependence of the random variables h1 to hn. For example, if we assume that there is a Markov dependence, we think that we can obtain similar inequalities, and so we also be able to consider some in the regression framework that the errors are not independent, but with some dependent structure. So we have many work to do with this inequality, I think. Okay. So thank you for your attention.
Thank you, Antoine. So are there some first question?
I do have a question. Can I start?
Go, Geoffrey, go.
Sure. Do you recover the bounded case with the equation? It looks like yes, right? If your random variable, they're all bounded, it looks like you recover up to constant the same concentration inequality as Talagon. I mean, Klein and Bousquet version, right?
In the Gaussian part, but we have this part, which is in fact the fact we have only assume that we have a moment of order p.
So it will be 1.
But as in the Foot-Nagiaev inequality, if we consider the bounded case, this one we always have an additional term.
Okay, I see.
But
and another, I think I got it. Another question, I do not have any intuition where does this Vn formula comes from with the partial sum. Do you have any quick explanation? Why does it appear?
Why EK appears?
Yeah, those sum, exactly.
It's not only technical, but it is due to the method I used to obtain these inequalities. The method is based on some martingale techniques associated with some comparison inequalities in the spirit of Pinelli's inequalities. I don't know if you know, but the comparison inequalities generalize the Hoeffding inequalities. Hoeffding inequalities compare in sort of it's for bounded random variables, but Pinelli show how to Pinelli and Bentus show how to obtain an Hoeffding-like inequalities for unbounded random variables. And using this fact, these quantities appear quite naturally. But
okay, thank you.
Okay, I ask my question to you later. Let's go to the second talk, André.
Excuse me, can I ask just one question?
If you want, you can.
Yeah. So, thank you. So I actually read this paper, and I also read the paper written by Johannes Lederer and Sarah van der Geer. So in that paper, you quoted that paper, and it seems like they also has the same assumption, the finite piece moment of the measurable envelope, right?
Yes.
So can you tell me, like, can you compare those two results, like, briefly? like what's like maybe just abstractly, like what's the strength of your inequality compared to lateral one?
In their paper, they use a truncation argument associated with Lagrange inequalities. They control the bounded part with the bounded case and the Riemann term with only this assumption. But it is somehow complicated to compare the two results themselves. However, what I can say is that the deviation, as I said, the deviation is not around E of z. We have this extra term, which implies some constants which are not, which are very unpleasant in the white bond, and in fact, we do not have the white behavior. Also, we do not have in the result. We do not have this behavior in the moderate deviation that we want to obtain. That is quite naturally to want to have this behavior for in the moderate deviation.
Oh, okay. Thank you very much.
Okay, thanks a lot also for the presentation. Actually, we will now introduce the second speaker. Geoffrey Chinot is a postdoctoral researcher under the supervision of Sarah van de Geer at ETH Zurich. His main research interests concern learning theory, high-dimensional statistics, robust statistics, and also robust learning based on median of means types estimators. He will present a contribution on Adaboost and robust one-bit compressed sensing, I think, joint work with Felix Kuchelmeister, Matthias Löffler, and Sarah van de Geer. Please. Thanks.
We don't hear you, Geoffrey.
Sorry, I didn't notice I was muted. Okay, great. Thank you for the introduction. So it's perfect that you were talking about Sarah because, as you said, Sarah is part of this project. So this is a work I've done last year with my co-author at ETH, and I'm going to talk about Adaboost and robust one-bit compressed sensing. So if you don't know what it is, I hope have time to explain it. And I will, of course, talk a little bit about concentration inequality because this is the aim today. So please do not hesitate to interrupt me if there is something that is not clear or if I go too fast or too slow, okay? So that will be maybe more statistic oriented, I would say, compared with the previous talk. So I will start, I cannot change. Oh, okay. I will just come back on something very simple, a very learning task that is binary classification. So here you can observe images of cats and dogs. And there is a simple problem in statistical learning, binary classification. We want to, given an image of cat or dog, predict the label. Okay, so you give me an image and I want to predict either it's a cat or either it's a dog. Something very common in practice, something we really need to do. And there are many ways to do so. And the state of the art is probably some algorithms that are based on neural networks or random forest or even Adaboost. Of course, today I will focus more on Adaboost. And there is something that is actually quite surprising when you look at the results that are obtained for this data set. So it's a data set of picture of the dogs and cats, and it turns out that when they train their algorithm and they test the algorithm on a data set, they can measure the accuracy of the learning rules. So the accuracy, for example, of the trained neural networks, of the trained random forest or Adaboost. And it turns out that the accuracy is very high. So for example, here for this data set, you have 97% of accuracy. So with a very large probability, I'm going to predict the good label. So if it's a cat with very high accuracy, I will predict that actually the image is a cat. Okay, but what does it mean? It means that if we use the Bayes theory, that actually the label noise has to be small. Otherwise, you cannot expect such a high accuracy. So this is the first thing I really want to emphasize here, is that in those data sets, the label noise has to be small. Otherwise, you cannot have such a high accuracy on the test set. But this is something that is not true only for this data set. There are many data sets that are really used in practice if we want to test algorithm that we're trying to develop or new architecture for neural networks. And it turns out that for many data sets, you have a really large accuracy. So in all those data sets, it means that the label noise has to be small. So we are in the setting when the label noise is small. Otherwise, we cannot have such a high accuracy. And a second feature that I really want to emphasize here, that is common for those three algorithms, is that they are all over-parameterized and they all interpolate. So what does it mean? It means that they have a lot of parameters. For example, in the neural networks, they have a lot of layers, a lot of neurons inside each layer, and the number of parameters is much, much larger than the number of sample. And they interpolate. What does it mean? It means that on the training set, I have zero training error. I predict perfectly. And the traditional wisdom of statistics is that normally interpolation is not such a good idea. Even if the noise is small, sometimes it's not the best. And today, actually, we are going to show that in the setting where the noise is small and the Adaboost interpolates, we're going to explain why Adaboost can work in this setting. So why overparameterized Adaboost works even when the label noise, there is label noise, but which is small enough, of course, and that we interpolate. Okay. So of course, I need the mathematical formulation of the problem. So I have n data points. So it's my data set that I'm going to use to train the Adaboost. So xi is my vector of features. Okay, so for example, it's my picture of cat that I can vectorize. It's in a vector in RP, and yi is my label. So it can be -1 or 1. For example, let's say -1 if it's a cat and 1 if it's a dog. Okay. And the model we consider here to model the notion of noise is the following. We assume that yi is the sign of xi transpose beta star, where beta star is the parameter we try to estimate. If I does not belong to a set that I call capital O, and otherwise, if I belong to this set capital O, we flip the label, okay? So somehow we want really all the time to observe the sign of xi transpose beta star because we want to estimate beta star, but there is some noise in the process and the label can be flipped. The label are flipped if the data is in the set of that I call capital O. So capital O for outliers, because we shouldn't observe minus sign of xi beta star, but we should observe actually the opposite sign of xi transpose beta star. Okay, so this is the model, and there is something very important here is that we do not assume anything on the set capital O. So it means that the set can be deterministic. I can just decide to, for example, take the first 10-1 and I flip the label. It can be random, different random scheme, and it can be even adversarial. Adversarial meaning that we can choose the set of flip point to make the learning task as difficult as possible. Okay, so this is the only we do not assume anything on the set O. Okay. And the last feature that I also want to emphasize is that we are in a high dimensional setting. Of course, we want to explain why Adaboost works when it has a lot of parameters. So here we assume that P is much larger than N. Actually, what we need is usually that P is larger than N log N, okay? Times constant, of course. And the question we want to answer is how we can estimate this parameter beta star. Okay, so far I do not assume anything on beta star, and because I want to explain why we make this assumption on beta star that will appear later, and I hope it will be quite natural. Tell me if it's not natural for you. Okay, everything is clear so far, I hope. Okay, so let's turn to Adaboost algorithms. So Adaboost for binary classification, probably in its simplest form, there are different variant of Adaboost. So I really don't have a lot of time today, so I'm probably not going into the detail of the algorithm. We can talk about it later if you want, but just it's an iterative algorithm where we have T iterations, capital T. So capital T will appear in the rest of the talk. So remember that. And then each iteration, what do? I compute some weight, and the weight is, we put more weight on the points when the points that make a lot of mistakes. So if a point has a high, makes a lot of mistake, I want to somehow focus more on this point, and I will put more weight. Okay. So each point I give a weight. Then I compute. I look for the maximizer of a certain loss function, and I update my parameter beta t. Okay, and I return tilde beta t that actually I should have called hat beta t, because there will be hat beta t in the remainder, the rest of the talk. Okay, so this is not really important if you don't know Adaboost or you don't really understand how it works. It's just an algorithm that is very, very used in practice, and it turns out that there is only very little theoretical result, at least non-asymptotic theoretical result on Adaboost. And the most important is the following theorem, probably. I mean, at least so far. So if we run Adaboost with enough iteration, so let's say that T is large enough than this quantity A that depends on M. I remember N in the size of the data set. So this is the size of points in the training set. P is the dimension of the parameter beta star I'm trying to estimate. The double bar O here, meaning is the size of the number of outlier, the number of flip label. So this is exactly the number of flip label. And epsilon here is the precision parameter that appears also here. So if T is large enough, we have that the following quantity here on the left. So the minimum over all data points, yi xi transpose hat beta t renormalized by its L1 norm. So we call this quantity the L1 margin. And hat beta t is the output of Adaboost at iteration t. We have that the L1 margin of the output of Adaboost is actually converging toward the max L1 margin. Why converging? Because I can always take T that is large enough, and then epsilon converges to 0. And in this case, this is exactly 1. And we have exactly the convergence of the L1 margin of Adaboost towards the max L1 margin. Okay, so if we run Adaboost with enough iteration, we're converging toward this weird max L1 margin solution. But it's quite intuitive why it works, because when we predict something at the end, we take the sign of xi beta. If beta is my prediction, I take the sign of xi beta, xi transpose beta. And of course, if it's very close to 0, it means that I don't really know if actually xi transpose beta is positive or not negative or negative. So I do not have a lot of confidence into what I'm predicting. But on the contrary, if it's really large, then I really think that actually, I mean, this product yi xi transpose beta is very large. I'm quite confident into what I'm predicting. I'm really thinking that it should be positive, and I'm predicting with high confidence. So if I take the minimum and the minimum is high, then I expect to have good performance. I predict with quite a lot of confidence. So I expect that this is a good estimator. So this is the intuition behind the L1 margin. And it turns out that actually this max L1 margin has another, we can just use duality argument to rewrite it as a different quantity. So this is the inverse of the L1 norm of what I call hat beta, where hat beta is the solution of the following problem. So this is the argmin of the L1 norm of beta over all beta, such that the minimum over all data point of yi xi transpose beta is larger than 1. Okay. So intuitively, we want a large L1 margin. Given this equation, what we want the this norm, the L1 norm of hat beta to be small. If it's small, then the max L1 margin will be large. And somehow to have this quantity small, we expect to use the L1 geometry. You see that the L1 geometry appears everywhere. L1 geometry meaning that the L1 ball. And this is why actually we gonna do some structural assumption on beta star. We assume that beta star belong to the unit sphere intersected with the L1 ball of radius square root of S. Okay, so I hope it's more natural now why we're making this assumption of beta. Beta is effectively S sparse. Now you may ask why I can take the unit sphere here. It's actually because we observe only the sign. So the scale of beta is lost into the quantization that we observe. Okay, so we observe the sign. So if I multiply xi transpose beta by a, let's say, the sign is still the same. Okay, so I can always work on the unit sphere. Okay, so beta star, this is what I assume. And now I arrive to probably the main result of the paper. If we assume that Adaboost is run with Gaussian iteration, and we assume that P is large enough, I really need this high dimensional setting, and that beta is in the unit sphere and its L1 norm is bounded by square root of S. When the xi or IID normal isotropic, so identity covariance matrix, then with large probability, I have the following. So here, this is the statistical error, the estimation error. So the output of Adaboost that I need to renormalize by the L2 norm because I want to compare it with beta star that belongs to the unit sphere. The estimation of error of that is bounded by the following quantity on the right. So in this quantity, we first observe the S log P divided by N. So this is something we have a lot in the high dimensional statistics, so people to the lasso, the dancing estimator for also many other sparse problems. And we also have a log n factor here. This log n factor, I mean, at least what I think is that it comes from the fact that the contamination is adversarial. And since it's adversarial, we always need to take the worst case, and that's why we have the log n factor appearing here. Now, if the exponent 5 is optimal, I don't think so. It's probably an artifact of the. And we have, of course, a number of flip points. So the number of flip points here appears in the parenthesis. And you can see that actually, if the number of flip points is smaller than the sparsity, I mean, the bound on the L1 norm, then the rate remains the same. So somehow the output of Adaboost is robust to up to S flipped data points. If there is more than S flipped data points, then the performance gets worse. Okay. So this is the rate that we have. And of course, we did some simulations, and it turns out that the exponent 1/3 that we have here that might sound weird for you is probably the good one. So on the left here, we plotted the estimation error and the log P over N to the power 1/3. It looks really to be the good fit. So it looks like 1/3 is the good exponent. And the same, the number of flip points divided by N, so the proportion of flip points to the power 1/3 looks also to be the good exponent. So 1/3 looks to be the good exponent. So we are probably optimal, at least modulo log factor. So the log P is for sure here, but the log N, we don't really know. Okay, so now I will maybe more talk a little bit about concentration inequality and the proof of the main result. So to prove this result, the main result, we need the tessellation result. So this is the following theorem that there is a different version for different setting in the paper from Discussant and Mendelssohn in 2021 about tessellation, and we adapt the proof for our setting that is a little bit different. So we set the parameter A that is positive, and we set the following eta. Okay, so it does not really matter what is written here. What we have is the following complicated formula that is written here. So if I take the infimum over beta that is in the unit sphere intersected with the L1 ball of radius A, that is intersected with all the points beta that are far innermost from beta star. So it means that the L2 norm between beta and beta star is larger than eta. Then the empirical loss, so the number of different signs that I predict, will be at least of the order eta n. Okay, so maybe it's a bit complicated, but what does it mean actually? It means that if I take a beta that is in the unit sphere and the L1 ball of radius A, if beta is large, is far from beta star, if beta is far from beta star in the L2 sense, so the L2 norm between beta and beta star is larger than beta, then the number of training errors that the training error that I make, the training mistake that I'm making is at least eta n. And why this result is very important is actually very simple. So by definition, the output of the Adaboost interpolate. So I take t large enough such that I interpolate the data set. So I have 0 training error. So it means that the sign of xi transpose beta hat t is exactly yi because I interpolate. So the number of training error that I do is exactly the number of flip. Okay, and here I'm going to assume that I'm I assume that the label noise is small, and I assume that the number of flip point is smaller than eta n. And in this case, the proof is almost over. Why? Because if the norm between my output renormalized of Adaboost and beta star was large, that will contradict the tessellation result here. So it gives you exactly the result we had here. Okay, but we are not completely done actually, because we need to understand what is the ratio of the L1 norm over the L2 norm. Why? Because if we know the ratio, we know what is the value of A, and we can finally use this result to conclude the theorem. And this is here that I'm going to use concentration inequality, even if this tessellation result there are a lot of concentration inequalities as well. So remember that we saw that the Adaboost output, if t is large enough, converges toward the L1 max, the max L1 margin. Actually, we can also rewrite it. It's a very simple exercise to rewrite that the ratio of the norm between the L1 norm and the L2 norm is equal to the ratio of the norm for this parameter beta bar. And beta bar, it has the following, it verifies the following two things. The first one is that the minimum over all data point of yi xi transpose beta bar is larger than 1. And its L1 norm is bounded by the following quantity. Okay, so maybe you don't remember, but the norm of hat beta here has been defined just here. This is this formula. So the minimum of the L1 norm under the constraint that is exactly the same that I have after. Okay, so I want to control the ratio of that. No, I have already the upper bound on the L1 norm. That is what I need. I need the lower bound on the L2 norm as well. So to get the upper bound of the L1 norm, I just need to upper bound the L1 norm of hat beta. And this is done in the following proposition with large probability. Here there is also some probability because of concentration, that the L1 norm of beta hat is bounded by square root of S plus the number of flip time log P divided by A to the power 1/3. Okay, so I'm almost done. I'm almost done to prove my main result, because I can use the tessellation result once I know once I know an upper bound on the ratio of the norm. Okay, I have the upper bound on the L1 norm, but I still need the lower bound on the L2 norm. So to have the lower bound on the L2 norm, there is a simple heuristic, a simple idea is that imagine that the L2 norm is very small. If it's very small, for sure, this constraint is going to be violent, in the sense that there will be at least one point I such that yi xi transpose bar beta is smaller than 1. And then it will contradict this inequality. So the L2 norm has to be large. This is how we are going to construct our lower bound. Okay, and this is done in the following proposition, and I will actually prove this result and show how we use the concentration inequality here. So assume that we have a point beta such that its L1 norm is bounded by delta. It satisfies always the same constraint here. Then with large probability, I have the ratio of the norm, which is exactly what I'm trying to control. Remember that the ratio of the two norm that I'm trying to control for the output of the Adaboost is exactly the same as this one. And this one satisfies the two structural assumptions that I'm actually considering here. Okay. So then with large probability, I can control the ratio of the norm. And this is delta Q log P over N plus an extra log factor. Okay. So now I'm going to talk more about concentration inequality. Maybe I haven't been enough talking about that, and I'm sorry about if you're here more for concentration inequality. I'm sorry. So how can we show this result? Okay, very simple idea. We take the constraint inequality. So for each point, we know that one is smaller than yi xi transpose beta. I take the absolute value and the triangle inequality. I get this equation, which is true for every z in RP. And I want to show. I want to use, of course, before doing so, I'm sorry. I need to do a net argument. So I define capital lambda A. That is a net, and it's a net of the L1 ball of radius delta intersected with the L2 ball with complicated radius. It's not really important. So to prove this result, we are reasoning by contradiction. I will maybe slow down a little bit to make sure that you understand everything. If I assume that this ratio is actually not small, but large, what does it mean? It's equivalent to assume that the L2 norm of beta is smaller than this quantity that I call rho n p delta times its L1 norm. Since I have an upper bound on the L1 norm by assumption of my proposition, I have also an upper bound on the L2 norm, and the upper bound on the L2 norm is delta times this quantity rho. This is why I take an epsilon a net of this L2 ball. Okay. Now I want to show that if there exists at least one point such that xi transpose z absolute value plus xi transpose beta is smaller than 1, then that violates that contradict the assumption I have here. And then this is for sure not true, and that will prove the main result. And of course, I need a result that is uniform for every z in the net and for every beta in the following set. So here beta actually plays the role of z minus beta here. So z, since I take a net, the L2 norm of z minus beta is smaller than a, and its L1 norm is smaller than the sum of the L1 norm, and they are both in the L1 ball of radius delta. So I've got the 2 delta here. Okay, so this is what I want to show. I want to show that there exists at least one point such that this is true. This is the goal, and if we can prove that with high probability, then we are done. And here you see that we need a supremum, so we need some concentration result. So how we can do that? We can define two quantities, G1Z, J1Z, that depends on Z. It's the set of points such that this quantity here, xi transpose Z, absolute value is smaller than 1. And the same for J2 beta, but this time it depends on beta. It's also smaller than 1. And I want to show that there is a common point, not only one for the set and J1 and one for the set G2, it has to be the same point. If it's the same point, then for sure there will be one point such that this inequality will be not true. And then that will show the result, that will show the result by contradiction. And to show that there exists at least one point, the idea is just to show that there is at least k point for the first one and n minus k plus 1 point for the second set. If there is at least k point for the first set and n minus k point plus 1 for the second one, for sure there is at least one common point, okay? Because there are in total n points. So this is what I want to show. I want to show this one, and of course I still need a uniform result. So I need to take the minimum over the net and the infimum over the set I had. If I'm able to show,
Geoffrey,
yeah,
please be finished in about 12 minutes.
Look, it's my last slide.
Great, thanks.
So how I can prove that? So the first one, I can use a Bernstein inequality and a union bound. So it's something quite common. And for the second one, you need to control the sum of indicator here. And to control the sum of indicator, I could use the bounded difference inequality for concentration, but that will give suboptimal rates. So instead of having the 1/3, I will have the 1/4. What I do Instead, I do generic chaining. So I use, for example, the result for Discussant in 2015 that allows to control the quadratic process here. So the supremum over the L1 ball intersected with the L2 ball of this quadratic process. And this is upper bounded by A2 to the square. Why? Because this is actually the expectation of that. So if we center this process, what appears, plus the complexity term here, A1 square log P over N plus the deviation. So they are also cross term, but they're neglectable here in this case. So to conclude, to prove our main result that we obtained with my co-author, we need many concentration results. So we need in the tessellation result that we did not present. In the last proposition, we need generic chaining, Bernstein inequality. And actually all those results that I did in the IID setting, where the xi are normal, random variable, you can generalize it to heavy tail design. But in this case, of course, you cannot use generic chaining anymore. And in this case, you need to use different tools. And for example, you can use all the small ball machinery that has been developed by Kolczynski, Mendelssohn, Oliveira, all this machinery that is very powerful and very useful, but it will give worse error rates in the sense that instead of having 1/3, you have 1/4. And last but not least, I presented everything for estimation error. So I was controlling the L2 norm between the output of Adaboost and beta star, but I can also obtain results that are actually the prediction risk. So how I can predict well, okay? And in this case, when X is Gaussian, this is equivalent to the estimation risk because of the Grothendieck equality. We'll call it like the Grothendieck equality. But when it's heavy tail, you can also obtain prediction result for heavy tail design that is not only Gaussian. And of course, I would like to obtain some lower bounds to see that if our bound is optimal. I think it's optimal up to log factor, log n factor. And I will stop here. And I'm sorry, I've been slower than what I expected. I did it 4 times today, it was perfect, but of course, with the adrenaline, always slower. So thank you for your attention.
Okay, thank you a lot. Thanks. Virtual clap. I would say, is there any special question from the audience? We can take one.
Can I ask a quick question?
Please.
So thanks for the talk. It was very interesting. So I have a basic question, just to make sure I understand the context. So if I understand it right, your version of Adaboost is giving you a linear classifier at the end of the day because you're using the beta from the last interaction, right? The version I know of Adaboost actually combines each of the betas, each of the linear classifiers, so that the final classifier is not linear, I think. And so my first question is, yeah. Yeah,
sure. So it's not linear in the sense because normally you use weak learning rules and you kind of aggregate those weak learners, right?
The usual version.
Yeah. So actually, I said it's in this simplest version, but Telgarsky proved this convergence result for other kind of Adaboost. And actually, all our theory works once you have. So if you give me an algorithm, so it's not necessarily Adaboost, but or other version of Adaboost. If it satisfies this inequality, then I can give you statistical guarantee for that. So it means that there are many algorithms that it starts to getting popular in the community that there is some implicit bias in the algorithms, and you converge towards precise solution. So for example, neural networks, linear model, and in the case of Adaboost, you can show that other different version of Adaboost also converge toward this max L1 margin. So in this case, you can say the same.
Okay, all right. That was my second question. Thank you.
Thank you.
Thanks. I give now the word to Sandra. Thanks.
Okay. So
should I stop sharing my screen maybe?
Yes. Now, because I will know. Okay, so it's my pleasure to introduce Gábor Lugosi from Universitat Pompeu Fabra in Barcelona. I was seeking for some information on his webpage, but I could not find a curriculum vitae, but I found a very nice cover of Toxic by Britney Spears, where we play saxophone, I guess. And but okay, this is not the point. So we are very, very glad that Gábor has accepted the invitation to be the discussant here of this workshop, of this web seminar. He is very well-known prominent researcher on mathematical statistics, in particular in probability. And in particular, we all know a book which is very related to what we are discussing here, which is Concentration Inequalities, non-asymptotic theory of independence in collaboration with Stéphane Boucheron and Pascal Massard, but also other books on pattern recognition and prediction and density estimation and so on. Another important contribution he has in the academic field is his works as editorial board of very important journals such as Annals of Applied Probability, Journal of Machine Learning Research, or Probability Theory in Related Fields. So, okay, it's it's my pleasure to introduce you, Gábor. Thank you very much for accepting this invitation, and please, okay, it's you.
Thanks so much, and thanks for the two really nice talks. So let me. I have a few slides. These are so I have maybe n slides here. N-1 are about these moment inequalities that Antoine was talking about, and one is about Geoffrey's talk. So, but I will have a few questions and remarks to both of you. So, these slides I recovered from an old course of mine that I was teaching from this book that you mentioned, the Concentration Inequalities book. So let me tell you how we approach this problem, and well, not just us. How there's this beautiful approach that's based on the entropy method that Michel Ledoux invented, and then how we arrived to moment inequalities, and how it gave us inequalities for moments of empirical processes, and how unsatisfactory they are, especially if we compare them with Antoine's results. So I will let me go through really quickly of the build-up of our approach, and of the entropy method approach, and then what we end up with if we follow this program, and then I will compare that to one of Antoine's inequalities. Okay, so that's what I'm planning to do. So let me start with my favorite inequality, the Efron-Stein inequality. Can you see my cursor? Okay. So the Efron-Stein inequality is really a general inequality for arbitrary functions of n random variables, and I'm going to do this slowly because I think every young statistician should have this inequality in his or her pocket. This is a really nice tool, extremely useful. So what it says is that if you have independent random variables, arbitrary distribution, just independent, they don't even have to be IID, and we have an arbitrary function of these n random variables, and now we plug these n random variables into that function, then we get the real valued random variable z. Okay, so the Efron-Stein inequality says this, that the variance of this complicated function of independent random variables can be bounded by the expected sum of these conditional variances, where this variance is only with respect to the ith variable. So we can fix all the n-1 remaining variables and just look at what the conditional variance with respect to the ith variable is. Okay, so this is an extremely useful inequality. Here's an equivalent version of rewriting it. So if I introduce zi prime, this new random variable, which is exactly the same as z, except that I replace the ith random variable by xi prime, which is just an independent copy of xi. Okay, so I keep everything fixed. I replace the ith random variable by xi prime. Then the variance is bounded by 1/2 times the expected value of the sum of the square differences between z and zi prime. Okay, so what this says here is by how much does this complicated function of many random variables change if we flip one random variable, if we redraw one random variable. And often this is really easy to understand, right? Even if you have a really complicated function, often you can very simply bound what happens if we just change one random variable and we redraw one random variable and keep everything else fixed. So this is extremely useful. There are many immediate corollaries of this that are otherwise really difficult to get. Okay, so that's Efron-Stein. And from Efron-Stein, you can actually prove the Gaussian Poincare inequality, which is a classical inequality. It can also be proved by other means, but it comes from Efron-Stein. This can be proven in 2 lines using the central limit theorem. So what it says, everything is in the book. So what it says is that if now we have a vector of standard normal random variables, okay, so these are IID standard normals, and now I take a function, arbitrary function of these random variables, let's say differentiable, then the variance of this function is bounded by the expected gradient squared of this function. Okay, so this is the Gaussian Poincare inequality. Again, very useful. There are many beautiful immediate corollaries of this. If you want to bound fluctuations of functions of a standard normal random variable, you can always look for this inequality just to get a grasp of what you can expect. Okay, and an immediate application of this is for a maximum for Gaussian process. Okay, so if we have now a centered Gaussian process, let's say continuous, and we look at this random variable, which is the maximum. Okay, so we have an arbitrary Gaussian process. The only thing we assume here is that these are jointly Gaussians. And we look at the maximum of this process, then the variance of the maximum is bounded by the maximum of the variances. Okay. So in the Gaussian world, bounding the variance of the maximum of the process is really easy in the sense that you can just look at the one-dimensional variances. If you can bound that, then that's going to be an upper bound. Okay, and I'm not going to go through the proof, but this is the proof. It's just an immediate corollary of this inequality. Okay, so you can just use it for the maximum, do an appropriate linear transformation, and it just pops out. Okay, because the maximum is a Lipschitz function. Okay, so that's the maximum for a Gaussian random variable. Gaussian world is beautiful. The variance of the maximum is bounded by the maximum of the variances. This is as good as what you can hope for. Okay, now if we want to go beyond variance, then and this is the basis of the entropy method, we can define the entropy of a non-negative random variable as the gap in Jensen's inequality. Okay, so we look at this function x log x. That's a nice convex function. We know that this is always positive, right? Because the expected value of a convex function minus the convex function of the expected value is always non-negative. And let's just define this gap as the entropy. Okay. Now it turns out that some classical and also very easily provable inequalities in information theory, in particular Hans inequality, implies that this entropy is subadditive. Okay, so what does this mean? The entropy of such a random variable is bounded by the expected value of the sum of these conditional entropies. Okay, so now recall this looks exactly the same as Efron-Stein form, right? The only difference is, I'm sorry for jumping up and down. The only difference is that here we have instead of x log x, we have x squared. Okay, so if you replace here in the subadditive in the definition of entropy, if you replace this function phi by x squared, then what we get here is exactly the Efron-Stein inequality. Okay, so you can these are Efron-Stein inequality and subadditive of the entropy. These are very close cousins. All right. And once you start from this, you can also very similarly to the Gaussian how you can prove the Gaussian Poincare inequality from the Efron-Stein inequality. You can prove the so-called Gaussian logarithmic Sobolev inequality, starting from the subadditive of the entropy. Okay. Again, this is the proof. It's really just I'm not doing it. It's just it just uses the subadditive of the entropy and the central limit theorem. And what it says is that now if I have any function of an IID Gaussian random variable, so now this this subadditive of the entropy, I forgot to emphasize, this is true for any functions of independent random variables. Okay. Now we are back in the Gaussian world. If x is a standard normal vector, then the entropy, and then I take any function, any differentiable function from Rn to R, then the entropy of z squared, well, I have to make this a non-negative function. Remember, the entropy is only defined for non-negative random variables. So the entropy of z squared is bounded by twice the expected value of the gradient squared. So again, this is very similar to the Gaussian Poincare inequality. In fact, you can prove that this is a strictly stronger statement. So this actually implies the Gaussian Poincare inequality. Okay, good. So now going from the Gaussian logarithmic Sobolev inequality, now it's not difficult to prove the so-called Gaussian concentration inequality, which goes back to this paper that Antoine mentioned, Tsirason, Ibragimov, Sudakov, who proved that if you have any Lipschitz function of Gaussian random variables, a standard Gaussian random variables, then we have this beautiful concentration inequality, which is dimension free. Okay, so here x takes values in Rn, but n doesn't appear anywhere. The constant in the exponent here is just the Lipschitz constant. So if we now apply this to the maximum of a Gaussian process, okay? So again, z is now the maximum of a Gaussian process, and sigma squared is the maximum of the variances. Okay? Then we have this beautiful exponential inequality that says that if we want to bound the difference between z and its expectation, the probability that this exceeds some value u is bounded by, and this is exactly as if we had a single Gaussian random variable with variance sigma squared. Okay, so again, the Gaussian world is as pretty as it gets. This is a beautiful inequality, and this is again Antoine was talking about this. Okay, so this is the Gaussian world. Now, what happens in general? So this was the subject of Antoine's talk. Suppose that we have an index set. Let's just assume that it's finite or countable. It doesn't really matter because you can always approximate if things are sufficiently regular. So so we have these vectors, the XIS's, and now this is how we define the empirical process. So these are independent copies of the same vector indexed by t, and now we just take the sum of these independent vectors, and we want to look at the largest coordinate of this vector. Okay, so this is the supremum of an empirical process. This is what Antoine was talking about. And now just as a start, we can look at what we can say about the variance. So remember, in the Gaussian world, the variance of z was bounded by the variance of the maximum was bounded by the maximum of the variances. Now, this is not true anymore. So you can play with the Efronstein inequality. I'm gonna skip these two slides where we play with them, but let me just show what kind of inequalities you can prove by Efronstein. You can prove that the variance is bounded by V, this quantity here that we call the strong variance. So and you can prove another by a little bit more refined argument. You can prove that the variance is bounded by the sum of these two things, which we call the weak variance and the wimpy variance, which is even weaker than the weak variance. So what are these? So the wimpy variance, this little sigma squared, is just the supremum of the variances, right? Everything is zero mean here. So this is just the maximum of the variances. This is what showed up in the Gaussian case. So in the Gaussian case, the variance is bounded by just little sigma squared. Okay? But in the general case, we have this other term, capital sigma squared, or even worse, we have this capital V, which are always bigger than the maximum of the variances. Okay, so the wimpy variance is smaller than the weak variance, and it's smaller than the strong variance, and the difference can be huge, right? Here we put the supremum. Sorry, so here when you bring the expectation outside, clearly this can be much worse. Okay, but this is the best kind of inequalities you can say. So this is just the first indication of why empirical processes are much harder than the Gaussian case. Okay, so even understanding the variance is a non-trivial issue. Now you can prove that if the expectation of the empirical process is small, then you can control this weak variance, this guy, capital sigma squared, because it's bounded by a constant times the expectation plus sigma squared. If the xi's are IID, then it's just twice the expectation plus sigma squared. Okay, so you can sometimes say nice things, but if this expectation is not small, and often there's no reason to expect that to be very small, then we have to pay. Okay, at least in these inequalities. All right. So now, what about exponential inequalities? Now, this is Talagrand's inequality that again Antoine mentioned, that says that if the process is bounded, then life is kind of good. Then we have a beautiful exponential inequality that reflects of what we expect from this variance bound, right? From the bound of that since the variance is smaller than the sum of the weak and the wimpy variances, this is kind of the best thing that you can hope. Like this looks exactly like Bernstein's inequality, where you replace the variance by this variance proxy, which is an upper bound for the true variance. Okay, so this is basically the best you can hope for, and this, of course, Talagrand's inequality is incredibly powerful, and it has many applications. But as Antoine pointed out, of course, here this requires boundedness. So if you don't have boundedness and the process is not Gaussian, then the problem complicates. So there's an even sharper version, that's Bousquet's inequality. I'm just going to skip that. Antoine mentioned this. So what can you do if you want to work with if you want to get moment inequalities? Let's say we don't have boundedness and we don't have Gaussianity. We just want to get bounds for moments of a function of independent random variables. Now, what you can a possible approach is to generalize that notion of the entropy. Well, this is a common generalization of the notion of the entropy and the variance. Okay, we call this the Phi entropy. So if we have a non-negative function, then we can just define if Phi is a convex function, then we can look at the gap in Jensen's inequality. Okay, and now you can ask when does it happen that this entropy is subadditive. Okay, subadditive, just like the variance was subadditive, that's Efron-Stein's inequality, or that the entropy, the usual entropy, is subadditive, which was the basis of the entropy method, and it turns out that we can characterize when this will happen. So if this function phi is twice differentiable and one of the second derivative of phi is concave. So both x squared and x log x fall in this class, but also x to the power p for any p between 1 and 2 satisfies this. So we can now work with this type of phi entropies, x to the power p. Okay, so instead of x squared, that was the variance, or x log x, which was the usual entropy, now we can look at the entropy of a non-negative random variable when the entropy is defined in terms of this x to the power of p function. Okay, and here think about p being close to 1. That's somehow the interesting range. Okay, and starting from this inequality, and I'm not going to go into the detail, we could prove a generalization of the Efronstein inequality. Okay, so what does this say? Remember, f is just any function of n independent random variables, and this zi prime is the same as it was in Efronstein's inequality. So we take our original random variables, but we replace the ith one by an independent copy. Okay, so we just change the value of one random variable. Then this is zi prime, and now we look at the sum of the square differences. Okay, there's a positive part here because of technical reasons, right? But let me just say that the Efronstein inequality says that the variance of z is bounded by expected value of v plus. That's exactly what the Efronstein inequality says. Okay. Now, what you can prove is that for any q greater than or equal to 2, the qth moment of the positive part of these deviations, z minus ez, is bounded by square root of q times the q halves moment of this random variable. Okay. So if q equals 2, then this is just the expected value, and we get the Efronstein inequality back. What this says, what this inequality, this generalized Efronstein inequality says, is that if we can control the higher order moments of this random variable v plus, then we can automatically obtain moment inequalities for any function of independent random variables. Okay, so for example, if the function has bounded differences, by changing one value of the function doesn't change the value of the function by too much, then this will be a constant, and what we get is that the qth moment is bounded by something of the order of square root of q, which is the moment of a Gaussian random variable. So we get these Gaussian concentration inequalities for bounded random variables. Okay, if you don't have bounded differences, then we have to understand this. Okay, and that's often not easy. So what did we get? So let me just show you an example of an inequality that we could get using this type of approach. Okay, now you want to try to understand what happens.
Yeah, well, just let me ask you, just if it's as time is running, just take like couple of minutes. Is that possible? Okay, no problem. Thank you.
I arrived to where I wanted to. Sorry.
Thank you.
So let's now look at the maximum of supreme of an empirical process, just like Antoine did. Let's say zero mean. So the inequality we could prove has this type of form. Okay, so you have this square root of q. Okay, that comes from here, right? Which is that the square root of q should be there because that's what gives us the Gaussian case in the Gaussian times, and now we have this weak variance and wimpy variance, and now we have the qth moment of the maximum multiplied by q, and this is really difficult to control in many cases. For example, for Gaussian processes, you can check this is way too weak. Okay? If you compare this with Antoine's inequality, the same thing can be bounded by, now the strong variance is gone, which is beautiful. Instead of that, he had this mysterious Vn term, which he claims to be smaller than sigma. I believe him, but I have to admit I don't understand what that thing is. And then he had this other term, which also looks much better. But I would like to ask him to kind of explain what this n to the. I guess this is probably necessary as well. So you see, this is a much stronger inequality, and of course he had to work much harder. It's not, he didn't go through this somehow principled way where you start with very general functions of random variables, but he really had to go into understanding the intricacies of these empirical processes. So maybe if Antoine can help me understand what if you think that this is the final word, is this the right thing to do, or is there anything better than one can hope for? So maybe can we ask Antoine? I can't see. Oh, I can see you now.
Yes. For the first part, that the sigma plus Vn, I don't think so. We can have a better than this term.
You mean this Vn? Yeah, I do.
This Vn.
As you pointed out here, you clearly need something. Just because of the Gaussian case.
For the other term, I don't know if it can be ameliorated, but however, for some of it's a wide behavior, but I don't think we can have better constant, better in front of the other 1/q, but
I'm not worried about the constants. I'm worried about. I'm just asking if this is the right thing to have here. Maybe it is. I really don't know. And also the other question is that that was already a problem with our inequalities. That how do you control this in application? You know, when you actually use this, want to use this inequality. This envelope, the qth moment of the envelope, is this? Are there examples when this is easy?
When we have some a decay as a power type in tail for the random variables, I think this term is more simple. No, I don't remember. And so we have some case where it is much simpler. I don't remember, but
okay, no, it's not. I was just wondering if there are, I mean, it doesn't look immediately obvious of how to.
No, right.
How to handle it, but yeah, but at least it's a one-dimensional quantity. So I mean, there's no n in this term. So is this n to the 1/q? Is this necessary?
This one, I'm not. This one I'm not sure. It comes from the inequality for the sum of IID random variables.
Okay, then it's probably necessary.
Okay, I will shortly interrupt. I think for the discussion, shortly I would also ask Geoffrey if you wish to relate to anything what was said with the discussion related to your.
Sorry, I didn't understand your question. Can you ask it again?
I mean, in your presentation, which were related to inequalities, do you wish to relate to the discussion in any way, or we just give the floor also to public for questions?
No, I'm all right. I didn't have time to talk enough about what I wanted, but that's my fault, so it's okay.
Okay.
No, but I remember that Gábor said also he would have some question about
Here.
the presentation. Okay. So sorry, that was the next step of Gábor then.
Yeah, but we can.
I guess we can let Gábor finish. Yeah.
Okay, so now these are just some remarks.
That's one slide. Yeah.
Geoffrey's paper. So as I so somehow there's a great mystery in deep learning. Okay, as we all know, but that when people train deep neural networks, they just minimize the empirical. They just run the training algorithm until the empirical risk is minimized. But But in my machine learning class, I always tell people not to do that. You have to regularize because otherwise you will overfit. So there seems to be this notion of benign overfitting, that you can somehow overfit your data, but still the method generalizes well. And then there's been a lot of research, a lot of interest now trying to make sense of what's really happening. What is this benign overfitting business? And the consensus is that it's in the algorithm that where we have to look for, because clearly you can't just take any method that interpolates the data. You of course you can't expect any good performance. But if you use in linear regression, we were looking at that particular case in a paper with Peter Bartlett, Phil Long, and Alexander Ziegler, and then Geoffrey had another paper where he improved on our result, where in high dimensional linear regression we could show that that even though we interpolate, the usual way of computing linear regression is just not any interpolation, but the one that minimizes the L2 norm. Okay? And that in itself, just in some cases, not always, but gives enough regularization that somehow makes the generalization error well behaved. There's really exciting, nice work in other areas of machine learning. For example, this paper by Aurora Cohen, Hu, and Low, where they look at matrix completion when you want to like in recommender systems, you see a small matrix, and then the usual way of doing this was trying to find the best low rank matrix that fits the data, but it turns out that you can just run kind of deep learning gradient descent algorithms without any regularization, and it will provably work. So that's another way, and the reason that happens is that somehow as gradient descent explores the space of all possible perfect fits of the data, it starts with the low complexity ones, and then it will find a low complexity one, and that has a good behavior. So so my question to Geoffrey is that where does your paper fit in this whole thing in this world? Is so in a sense you
I completely agree with you. It's the question about the algorithm. Everything is in the algorithm, that it always selected some low complexity solutions. But actually, so for example, in your paper with Peter and I forgot the first name, Malong,
Phil and Alex.
Yeah, exactly. So you're actually giving up a bound when you look at the minimum L2 regularizer, and it's the take-home message is that if the covariance matrix has almost a low dimensional structure, you can expect to do something well, right? And actually, it turns out that we can do also the same for L1 for L1 and L1 minimum norm, for group Lasso minimum norm, for TV minimum norm. So this is a paper we wrote also with Sarah and Matthias, and all the time. So it works for two reasons. It works because it has a low dimensional structure. So the optimization algorithm is converging toward a solution that has a low dimensional structure, and that the noise has to be small. I mean, interpolate works when the noise is small. It makes sense to interpolate when the noise is small, right? And it's also the fact that the data set that we have in practice, for example, in those image recognition, they always have such a high accuracy that it's kind of true that actually the noise is small. It's not necessarily structure, but it has to be small.
Right. Though sometimes then it's not really overfitting. It's fitting, right? If the noise is zero, then it's fitting.
Yeah, of course.
So you have to have some noise to be able to talk about overfitting. So that's this last question on my slide is what happens if you have small but not the YI is The flipped yi's don't necessarily go to zero. Their proportion.
So this is the rate that we have, and this is also the question of lower bound. We don't know what is the optimal, so the minimax rate with respect to the contamination. It's hard because it's adversarial.
Right. No. Yeah. Here I was thinking about more like random noise.
Yeah. So there is this work from Bernoulli and Plan, where they have a little bit better dependence with respect to the number of flip labels, but they also consider a regularized version. So they do not interpolate. They have an estimator that is regularized. So it's different. Yeah.
So another question I had is that you assume Gaussian, though at the end you were saying you can do other distributions. So
yeah.
What do you mean?
So actually, we submit this paper to your journal, and Charles told us that we should generalize that for also distribution. And actually, yeah, this is true. You can do it, but the problem is that you cannot expect any result in L2 sense. You can only expect result in prediction, because the prediction loss is related to the L2 loss because of the Grothendieck equality. But in the general case, you cannot expect to have any result in estimation error. So we can do everything for the prediction error, but the rate will be worse. The rate will be worse.
Clear conditions and let's say small ball conditions. Would that be?
No, small ball is not enough.
It's
small ball is not enough. No. We really think that this is only for the Gaussian, or even sub-Gaussian. It's not obvious how to do, because we really need this Grothendieck equality.
Oh yeah. No,
but if you want result in prediction, then if you use all the small ball that machinery that I'm writing the revision, it looks like everything is going well.
Okay, great. And I want to say that I really was impressed by those inequalities where you have explicit dependence on the sparsity and on the number of iterations of the. That's really
So we think that it's sharp for effectively S-sparse, but with beta is actually really S-sparse, we can probably have faster rates. But this is complicated because the output of Adaboost does not give you an S-sparse solution or something that is close to the S-sparse. That's why we don't know how to do it.
Okay, thanks so much. I'm really impressive. Both of the papers are really nice.
So thank you very much, Gábor, for have contextualized very so nicely on concentration inequalities, and for these very nice questions and discussion with Geoffrey and Antoine. Now I think Andrzej wants to now open to public question to conclude. So Andrzej, please.
I also thank for great discussion and responses, but I would also open the floor to the questions. I'm sorry that I intervened, but usually, we are sometimes limited with time. Please, if anybody has any question. You can. Of
course, you can also write your question in the chat directly if you don't want to go public.
Yes. Or you can just unmute. Anybody can unmute.
I have a very naive question to Geoffrey, Geoffrey, sorry.
It's right.
Sorry, Geoffrey, to Geoffrey. At one point in when you it's very naive, so I'm sorry because I'm not I don't know a lot of the area, but at some point in your main result, you mentioned that you need P to be very large in front of N.
Yes, exactly.
Yes.
So
this seems intuitively it seems weird. I mean, to me, because it seems like people usually say, it's not good to have P very large, and you're asking P to be very large. So just to understand better this. Thank you.
So my answer would be twofold. So first, there is the first reason is that if you want to interpolate, you need the dimension to be larger. Otherwise, you cannot interpolate.
So the point is that the largest it is, the better you can interpolate. This is, and so the better.
Yeah, exactly. When the dimension increases, then you have more and more solution that interpolates, and then you can pick up one that's actually good.
Okay, this was really a naive question.
And the technical reason is also that you need a hyper concentration result for the Gaussian tails, and you need P to be large. So, and it's actually related to some property, so we call it the quotient L1 quotient property in compressed sensing community. I don't know if you have heard about that. And this is verified for Gaussian, but probably for other distributions. So.
Okay, so
but this is technical.
I also have a question. It's a curiosity, actually, more on the concentration inequality side. So when I look at the concentration inequality, like an Efron or an entropy with the entropy method, I ask myself always: is there any kind of hope or some, I don't know, direction in the literature nowadays that allow to extend this kind of inequalities to serially correlated data? So of course we saw that they apply to always to IID, no, independent sequence, but I mean, is there any hope or direction in the literature for going towards this kind of cases? Because at the end, I guess that perhaps not right now, but machine learning is also moving towards the need to analyze better time series or in general correlated data. So what is the stand so far? Do we have, it's complicated. This was a bad question.
Oh, it's an excellent question. I'm just not sure who you're asking, but of
general,
course.
really, I'm asking in general, you know, very general, guys. I mean, what can you tell about this kind of problem? You say somehow we can extend it, as Geoffrey did, and Antoine also, to some kind of dependence, but
so there are extensions to Markov processes, and there is definitely stuff in the literature.
So you have to ask for a structure. So you have really to ask for a specific model. So you have to ask for more. So you cannot just say it's, I don't know, an alpha mixing process or things like this. That's to be more structured in a way. This is.
I think Sandro might know more about this.
You know?
No. Yeah. Actually, I work on some stuff like that, but we have still some kind of dependence. Now I can tell you that some result holds for beta mixing process if it's this kind of result you want, I guess. And we have also, I mean, in the area I'm working on, we have some kind of dependence, which are on, it's like extensions on Markov dependence, but I'm not sure exactly we get the same kind of concentration inequalities you're getting here. There are Gaussian inequalities, but which are optimal in some sense, but they are not very precise. As for instance, they don't involve variance of the random variables that you get for instance. So this would be the simplest kind of Gaussian inequalities, I guess. I'm not completely a specialist on Gaussian inequalities, but so that's nice you ask this, because I can say that I'm working on something like that. Thank you very much, Emma. It was not combined between us, okay? It was completely
good advertisement.
It seems like Emma, it was like just not combined.
It's funny. I mean, I work a lot in time series. We also are starting to work on something like this, but we work with weak dependence. So something has, you know, we didn't know. Anyway, but yeah, I guess it's a kind of a topic that is taking a lot of direction, and it's really, these concentration inequalities are needed in so many different applications, and they just pops up these problems. And then in time series nowadays we have so many, so really a lot. So it was really, I was really curious to know, but nice to know that we are moving in, we do interesting things. So.
Absolutely. There's also other types of dependent structures that people look at, like you have negative dependence and stuff like that, or you have weak dependence, but maybe
Like association.
The graph is sparse and stuff like that. So
like association more. Okay.
association type, exactly.
Okay. Yeah.
So yeah.
Okay. So let's see if there are no other questions. Andre, do you have some question?
I would indeed have one small question.
Please.
Do those inequalities, I think in particular relates to Antoine's presentation, hold for the processes with heavy and light tails? Are there significant differences related to such processes, relating to those inequalities? I think that Antoine, if I remember correctly, you mentioned heavy tails at the end.
So sorry, I do not hear you.
I didn't hear you well. No.
So the question is whether the inequalities hold also for the processes with heavy tails.
When we have heavy tails,
yes,
the question. But when we have some only a moment of order p, for instance.
But in general, this is generalizable to any such process. In this case, you had actually unbounded, but yes.
When we have, I'm sure I understand your question.
Can you obtain a concentration inequality, for example, for data where you have only, let's say, p moments instead of having a sub-Gaussian behavior or sub-exponential behavior?
Yes.
Yeah, but the complexity term will be higher, I guess. It's like data going result from psi 2 to psi 1, you pay something. So I guess something would appear as well.
Okay, yeah. But we only so for this kind of process, we only assume that we have a moment of order p. We do not assume other things with p greater than 2, but we do not. For result with p between 1 and 2, the question I think it's quite complicated. I have some work on this kind of when p is between 1 and 2, but it's very it's a very complicated world, and we cannot say so much, I think, but I'm not a specialist. I just obtained with the method I use. I just obtained, for example, an exponential inequality, but it's very hard to compare in the literature because we have not so much results, and so it's difficult to say if it's a very good one or if what we can do in this area. So I don't, but I cannot say so much.
Okay. Thanks for the explanation. Is there any other question? Just ask for the audience.
Well, I would have one last question, but I don't want, because I'm not sure, because perhaps other participants which are not the organizer want also to make some questions, because otherwise I'm using all the time. So okay, well, okay. If there is nobody asking, I can ask my a last question, perhaps from my side at least. At some point, it was mentioned that Lipschitz functions are very nice when we just flip the effect of flipping only one coordinate of the function. We can control the difference. And I would like to know what if there are some works which have been done outside this scope. Because there are some functional, for instance, when we work on return times, for instance, I'm looking at how much time it takes for some cylinder to come back in the realization of the process. So I take an IID random sequence of random variable, and I look until the first time some pattern occurs. But this first time, I mean, it's a function of the realization, but it's not. It does not satisfy this kind of. If I flip only one guy in the past, it may completely change. So is there some method in this kind of situations? I'm asking this for any one of you guys. I don't know. That's my question.
Yes, of course, there's a lot of work on this. And so even the inequalities I was showing, you don't need the individual differences to be small. What you need is the sum of the squares is well behaved. So that's one thing. And then there are other versions where you know that with high probability, you can control it, or there are various papers on this. Yeah, absolutely.
Okay. So next, okay, I will try to find literature on that. What is the name? So it's like, okay, so what will interest me would be something like you said right now, like with high probability we can.
Already in Efronstein, right?
This is the way it is presented. Okay.
Yeah, it's the sum of the squares of the changes that matters, and then you take the expectation of that. So if you can control that, then the variance is well behaved.
Take the Bible, Sandro.
I didn't make my homework. Okay. Okay, thank you.
So I guess we can conclude, André. If there are no other further questions for our speakers, then from the side of the Young Researchers Committee of the Bernoulli Society, I thank everyone for participating to this very nice web seminar, our speakers, and thank you very much, Gábor, for your very nice presentation and explanation, and for answering also our questions, also side questions. And I leave the floor to André for some final remarks.
Just one final remark. I again thank the two speakers, Professor Lugosi, and to all the audience and the co-moderators naturally. But I add, I hope we will have access also to the PowerPoint presentations for also the others to be able to get insights into the discussion later. Naturally, the seminar was recorded. It will be put on the YoungStatS YouTube channel, so everything should be accessible to all. I again thank to all. Yes. So hopefully see you also, that you follow also the work of YoungStatS. In future, I mentioned 3 webinars that are coming up on symbolic data analysis next in October. So hoping to see you really soon.
Should we send you the slides at your, where should we send the slide at you? Okay.
You can also send it to us. And then
Okay, sure. Okay, perfect.
Great.
Thank you so much, everybody. It was very nice.
Thanks to all.
thank you, guys. A very nice evening
you.
to everyone.
Thank you very much.
Bye.
Thank you.
Bye.
Bye. Thank you.
Bye.